an F, I think.
There is an F in there. That's
Hold
correct.
Let me look for it.
Yes. In the meantime, I will already write down the solution or the answer. Oh, that's part of it. That's not it, by the way. I hope you understand that equations usually have an equality sign somewhere.
Yeah, so is it this?
It is my handwriting, right? The upper one.
Yeah.
Okay, yeah,
Yeah.
I agree.
It's very not legible.
No, I There you go. This is all of electromagnetism, classically, written in fully relativistic way. Now it looks very different from the Maxwell's equations, yes? Now, what I would like to do this first lecture is actually talk about the Maxwell's equations. And for the people who either are familiar with them or have to re-familiarize themselves with it, to give you a feel for what they mean, right? I mean, we can write them down mathematically, but there is, of course, a particular understanding that goes with it. Now, this is not meant, this lecture, as a full substitute for your electromagnetism course. We don't have the time. I want to pitch a little bit with you. How much do you understand about the Maxwell's equations themselves? Yes? So consider this as somewhat of a freestyle first half hour or so. And I will open the floor. Just tell me either a Maxwell equation or some notion or phrase or something from your electromagnetism course that you think is important, that you remember or that you've heard this morning.
Magnetic fields do no work.
Magnetic fields do no work. Okay, so let me just make a summary, yes? And then let's see if we can sort of group things together. And once we've done that, it's 20 minutes, 30 minutes, I'm going to tell you exactly when in our series of weeks we're going to do what. So we have sort of an overview. But I would like to hear where you are right now. So magnetic fields do not work. What does that mean, by the way?
That if you apply del operator to a magnetic field, the result is 0 if you dot multiply it.
Yeah, sorry, one more time.
So if you dot multiply the del operator with the magnetic field,
yes,
the result is 0.
That is a okay. That is a very mathematical way of. I mean, it's correct. Yes. So actually, let me make it a separate part here. Say that if you take the inner product, the del operator with the magnetic field, you get 0. Or saying the same thing in a different language, you take the divergence of the magnetic field, it is 0. That's a mathematical statement, and now all of a sudden you say magnetic fields do no work. Now how is that connected?
Well, because this del operator is the position derivative of magnetic field.
Yes.
And if that's if you see it as a force, I mean, by the definition of work, it's like the x derivative of the force.
I'm not seeing it.
So if you integrate the force over a line,
yes,
that's work.
Agreed. Yes.
Yes, and then you can see it from here. If you're taking the position derivative of magnetic field, and that's 0.
Here's your definition for work. Yes.
Yes, and if
now you say that, and all of a sudden this is 0.
Yeah, if you put dl on the other side.
Something like this?
Yes.
Aside from vector issues, because I now have a vector on one side and a scalar on the other side, so I'm doing something wrong.
Well, f is 0.
Why is f 0?
Because
Oh, that's not f, that's a b. And by the way, the statement is not that b is 0. The statement is its divergence is 0.
Yes. So like, no, the b is not 0, but the divergence of it is 0, which you can see.
I'm not teasing you, I'm seriously not seeing it. You have an expression here that you want to say this will be 0.
Yes.
And you want to use this, and this has a b, this has an f, and then you say b is 0, but b is not 0, because the divergence of b is not 0. I agree that if you don't have a magnetic field, b is 0, it will do no work. That is correct.
Does that mean that just the magnitude of all the vectors stays the same? Like you don't have a sink nor a so like I don't exactly know if that's the way why you say that there's no work, but okay. I know that magnetic fields can't accelerate particles and like can't.
No, they can.
Can't they?
They can.
Magnetic fields. I thought it
Well,
was.
But
they
only
can
if they-
change
Oh, they
direction,
can
so
change
they
the
can-
direction, but they
Yes.
cannot like
Yes.
make them go faster.
Of course.
Yeah,
Now,
sorry.
oh, no, that's fine. But
Backtrack.
this is why we have to be very clear about these things. Yes. What would it be nice if maybe one of the tutorial exercises is to actually show that this is the case. Okay, so we will actually go and do this. I was slightly teasing. Of course, I know where you were going, but it was certainly not very obvious from those two equations alone. You have to do a little bit of work to get there. Okay, so yeah. Okay, I will try better with my jokes later. Okay? This one was non-scripted. Okay, anything else about? So you mean both of these are true statements, by the way. And yes, you are right; they are connected. Anything else that people might remember from electromagnetism or from general understanding of physics?
You can turn electric field into a magnetic field and vice versa.
Okay. Something like this, right? You can turn electric fields into magnetic fields and vice versa. Yes, correct. Anything else? I'm sure the prerequisites for this course are electromagnetism. I'm sure you picked up something there.
They are almost completely symmetrical, but not really.
Yes. So E and B, you mean, right?
Yeah.
There is a certain amount of symmetry, which is interesting, because this statement says you can turn one into the other, and if they are symmetric, you would probably. We're a little iffy right now on the definition of symmetric, but I know where this is going. But that you can turn E's and B's and B's into E's, and if that will be fully symmetric, I guess you would think.
You would still have the same equations.
Yes.
But you don't.
But you don't.
have monopoles in magnetism.
Exactly. Yes. That is actually again this statement that there's no magnetic monopoles. So I mean, what we're going to see today already is that you can turn E's into B's and B's into E's, but not as easily into each other. This is sort of the symmetry Giovanni is talking about. You can turn them into each other, but not quite under the same rules. So they're sort of the same-ish, or they obey the same rules, but not really, really, really. Anything else?
The electric field does not rotate if there's no magnetic field nearby.
One more time. It does not rotate, or?
It does not rotate if there's like no magnetic field nearby or something. Isn't it like the care of the electric field is 0 if there's no magnetic field?
Yes, that is correct. This is probably the deformation that I have, that I understand the mathematical expression better than the verbal one. This is actually true. This is one of the Maxwell's equations. This is one of the other Maxwell equations. Okay, anything else?
If charge accelerates, it emits light.
Yes. Accelerating charges emit light, that is correct. So classically when people found out about this is when they first realized that not only what light was, but also how you can produce it. Yes, you have to accelerate something. It's not fully true, because then quantum mechanics came along and everything, which says you can also make light by, having difference in discrete energy levels, and the difference in energy has to be emitted in some form, which doesn't really have to do with acceleration of particles. But this is the first idea that people knew where light came from to begin with, not just practically but fundamentally. By the way, speaking of light, I will add this one on my own. Light, of course, is an electromagnetic oscillation or deviation. Now I'm going to call it an oscillation. I want to stress, I don't say that light is always a beautiful sign or a color sign, yes. Just any deviation, any time that the electric field and the magnetic field change in a particular way, your eyes as a biological fact are able to pick that up. Now to me already that was super interesting, because if I hold a magnet here and it has some magnetic field around it, I can look as much as I want. I will not physically, or by biological eye, will not be able to pick up the magnetic field, agreed? Yet if I start shaking the magnet, and therefore I start shaking the corresponding magnetic field, all of a sudden my biology starts picking it up. So, hey, wait a minute, there's something coming to my eye now. That to me is super interesting. We are, as a biological fact, we are insensitive to magnetic fields and electric fields, but we're not insensitive using our eyes for the oscillations, the moving of these objects. To me, that's interesting. By the way, the same holds for sound, right? I mean, if you hold very quiet, aside from air conditioning, we are not able to hear air unless it starts moving. Yeah, sound is literally the motion of air molecules or so, and only when they start moving is when you start hearing. That's very similar. We cannot hear air unless it starts moving. We cannot see electric fields and magnetic fields unless they start moving. All right, that was a huge discovery in history, by the way, that people were investigating electric fields and magnetic fields, and then from mathematics alone they found, wait a minute, if you do this such and such and such, then apparently we get something that resembles all the rules of light that we had studied before without ever realizing what it was. Right? It was a huge discovery that light was actually connected to electromagnetism. So that's very nice. Anything else?
And the electric flux through a Gaussian surface is equal to the charge within over atom.
Okay, so there will be something like this is what you mean?
Yeah.
Yes, it should be circular integral. That's correct. Is this familiar to you, this one, this for instance? Yes. Right. It literally just means that if I have a bunch of charge here, and I want to know what the electric field is of this bunch of charge, the only thing I have to do is draw some closed surface around it. And then this law tells you that if you add up all the amount of electric fields sticking through that surface, that total amount equals up to an epsilon 0, the full amount of charge within. So that's true. This is one formulation of Gauss's law, or if you will, this is Maxwell's first equation. Maybe not written in form that you recognize, but that's why we're here. Is that about it?
This is the integrated version, right?
I think it's also something like the kernel of the magnetic field is equal to times 0 times J or something.
Yes, this is where you expose your Greek heritage, because we would call mu, but I guess mu is, in Greek alphabet, is what you would call n, right?
Exactly. That's like in Greek it's called mu.
Okay. Now you phrase it saying it's m times j. M. Oh yeah, mu. Then I thought mu is the Greek letter for m, but then again, what do I know? Yes, this is another of Maxwell's equations. It's actually wrong.
I think there's like a plus.
Yeah, there's a plus something indeed.
Time derivative of electric field times some constant.
Yes. It's not wrong because you're saying it wrong. People started with this equation and only later found that something must be wrong. And then we're going to actually also do this today during the story. We're going to show that this has to be there for reasons of pure consistency. Mathematics enforces that part to be there. Now, the good, that's Maxwell's fourth law. So which ones do we have by now? This is Maxwell's second. This is Maxwell's third. There still has to be added something. Yes, in fact, that is already encapsulated in this part. So we have Maxwell's second law, there's a third law, here's the first law in a particular way of writing, here's the fourth law. So we're already done really. I mean, we have almost everything on the board right now. So in fact, maybe now is a good time to just summarize the Maxwell's equations if you've seen it before. Now, then let's see if we can connect all these things together. So I'm going to take these for now as known to you. Here's Maxwell's first law. It says the divergence of the electric field is equal to the amount of charge density. Maxwell's second law says the magnetic field, its divergence is 0. Third law says that the rotation or the curl of the electric field is equal to minus the magnetic field time derivative. And then there's the fourth law. That's actually this one here, which indeed says that the curl of the magnetic field is equal to the amount of charge flowing by, that's J, and how much the electric field has been changing in time. Those are the four Maxwell's equations. Good, good, good. I'm just asking, these are known, yes? All of you have seen this before. Everybody is clear on what the symbols mean. Everybody knows E means electric field, everybody knows B means electric field. Mu0 is a constant, epsilon 0 is a constant. Both have to do with how easy it is for electric fields or magnetic fields to flow through empty space, yes? So if you want, it's sort of like the viscosity of empty space for electric fields and magnetic fields. This is going to be extremely important. The Maxwell's equations are inherently vector equations, yes? It's not because we choose to write them this way, it's because nature itself has these vector properties assigned to them. So we have to be extremely clear that all these symbols are known to you. I'm sure everybody knows this operator, but do you know what we mean by this, for instance? What do I mean when I say that the divergence of a vector is number such and such? What does that mean?
Something like how, like if you have like the vectors, like the arrows, how much the arrows get bigger as you get away, or how much they get smaller?
That's correct,
so
yes.
How they change?
That's correct, absolutely. Divergence, yes. Not just of electric fields, but of things. The divergence indeed is a measure that if you would write the electric field in our case, this vector, in say arrows, right? There's a certain amount of size at every moment, at every position in space. Then the divergence means how much will these arrows be sticking out from each other at any moment, yes. You can sort of feel what that means, but the divergence, the del operator, is a spatial derivative in 3 dimensions. So obviously if that is some number, then that means that the object of which you're taking the divergence is not staying at the same position, yes. And if some number is positive, then obviously it means that this thing that you're taking the derivative of, the spatial derivative, if that is possible, it means they're moving away from each other. That's what it means. We will see examples in a moment, of course. So yes, I like to think of the divergence as, if you will, the sticky outiness of a vector field. Yes? Now here, you have a divergence that is 0. So what does it say about the magnetic field?
Uniform?
Not necessarily, no. In time or?
In position.
No, it can. I mean, I have typically a magnet, right? One of these, with a north pole and a south pole. Magnetic fields look like this.
But I mean just the moment.
Yes.
From a point. There's nothing known as a point magnetic.
That is correct. Does it follow from this? The answer is yes, actually, but let's see if we can connect the dots.
There is no sink source behavior.
That is the same statement, I agree. Can we express this in terms of stickiness, sticky outiness? Electromagnetic field line.
Every arrow that goes out must have
Well, yes, I mean, if there's two ways that something cannot stick out, yes? One of them is simply that the thing is not there. Which is true, because if you take the magnetic field to be 0, then certainly you will get something that is 0. But there's a second way, namely if as much sticks out as there sticks back in. Right? So the fact that nature apparently upholds this law is another way of saying that, well, whatever goes out the magnetic fields has to come back to itself. And that's what you see here in my example, that the magnetic field has to come back to where it came from at some point. Now, magnetic fields go from one pole to the other pole, right? But suppose that there was only one pole. Then any magnetic field line has nowhere to go. So it will stick out to and radiate into space or something like that, yes? This thing says, no, every magnetic field line has to come back. So obviously the only way that this magnetic field line can come back on itself is if itself will attract it back to itself. So this again, in the Vishaya, you're completely right. It's another way of saying there can be no magnetic monopoles. You cannot have a single north or south pole, because otherwise you would have a sticky outiness that is not compensated by, you have no sticky backiness, okay? Now that's what this thing says. So the Maxwell's equations, they really, I mean, if you really understand what this Bell operator means, you can really make something out of this, even without doing calculation. This is why I want to start with doing this. And I'm sure everybody can calculate these things, but let's see if we can understand what they physically mean. All right, moving on. Oh, by the way, here's also where you see Giovanni's some symmetry, but not full symmetry, because there is sticky outiness of electric fields, but not of magnetic fields. So they sort of do the same thing, but not quite. And if you would be able, this was Alica was saying, right, connecting everything together now, is well, if something can, if you would be able to completely turn one into the other, then that means you should be able to turn electric fields fully into a magnetic field, or magnetic fields fully into an electric field. But at this point, the fact that they don't have a full symmetry, or if you look at this, that this one has a non-zero stick outiness and this has a zero one, means that apparently there's something blocking them from being completely transferable into each other. That's your almost symmetry, right? So that's good. Moving on, the third Maxwell's equation. Again related to this comment, that you can make them go together, that you can sort of turn one into the other. These two, the first two, don't make a statement about that. They just say how you can calculate each a piece. The last two equations tell you how you can turn them into each other, right? Because you have electric field on one side and magnetic on the other. So that means they should be related in some way. This one, Maxwell's equation, is called Faraday's law, tells you how you can turn into each other. How can you make a magnetic field out of an electric field? Or the other way around, how you can make a magnetic field out of an electric field. Now, well, you can see it here, right? Remember that I said, let's hold up a magnet and start moving it about or so? All right, that means I'm moving about the magnetic field in time. Then this law tells you, oh, but wait a minute, then that means it's as if there is an electric field around. It will be, your moving magnet will behave as if there is an electric field. That's what this one tells you. Now, how this moving about in time produces an electric field, I mean, how mathematically that works, how that electric field will look, is exactly determined by this particular shape, right? The fact that there's a curl instead of some other object. So that's what this one tells you. Then there's a fourth Maxwell law. Well, it's sort of the opposite statement. This one tells you if you shake about in a magnetic field or a magnet, you get back in some form or shape an electric field. Well, this one tells you, well, what if you start moving shaking about in time an electric field, right? So instead of shaking a magnet, I'm now shaking a charge, right? Then I'm shaking the electric field in that particular piece of space in time. Then this tells you, oh, well, then nature will behave as if there's a magnetic field around. But not quite. You know, if that were the case, if that was if that was everything, then this would have been fine. Yes. But there's this extra term. Can somebody interpret that one?
That can be seen also as coming from the fact that we don't have monopoles in the magnetic field, because since we have the possibility to have monopoles in the electric field, we can have a current. And we can describe this current by the J. If we would have also a magnetic current coming from the fact that we would have a magnetic field, yeah, then we would have in Faraday's law also an additional term.
I agree. Yeah, no, that's a good point. That's a good point. It wasn't what I was going for. It's physically absolutely correct. The fact that you don't have magnetic monopoles means you cannot put them into a wire and make them move. Yes. Mm-hmm. But this one tells you cannot have these magnetic monopoles, so you don't have single north poles or south poles. You can push through a wire and have something similar in this equation that tells you that if you have a current, you make an electric field. Right? J is the current, indeed. It's an amount of charged particles that are either pushed through a wire or maybe pushed, you know, through the corona of the sun or something like that, or close to black holes, these sorts of things. And that's what J means. It literally just means how much charges, not monopoles or magnetic monopoles, but just electric charges, are moving through space. And the first term on the right hand side tells you that too makes a magnetic field. Yeah? Now, so that's what that means. This equation really tells you that there's really two ways of making a magnetic field. Because either you shake around some electric charges, yes, and therefore you change the electric field, and therefore you will get a magnetic field. Or you can make a magnetic field by having charges flow through a wire or something like that, and then this will make a magnetic field. Now, question: aren't these two things really just the same? Because look, I can make an electric. This one tells you can make a magnetic field by shaking around the electric field. But you can make an electric field shake by making charges shake, right? Well, this one also tells you how that charges are moving. So how are these two things the same statement, just written slightly differently? That's a question.
Well, just from the wording, it's different. Charges and electric field are different things.
Yes. No, I agree. If I make a charge move, then this one tells you get a magnetic field. Fine, okay. But this one says, no, but if you make a charge move, you also make its electric field move, and that will make a magnetic field. So they sort of feel the same. It's just that this one starts with the moving charges, and this one has a middleman, namely the electric field that also has to change. But they're not the same though, and I want to make clear what the difference is. I can see that you have the answer here.
No, maybe.
Okay.
Is it not because the charge itself can be varied as well? How big the charge is?
That is a good point. Absolutely, yeah, absolutely, yes. I mean, you can vary the charge.
And then you're not moving specifically the charges.
No, that's true. I mean, you can have a charge sticking at one place, and it's not moving through space. You just make the charge bigger in some way or another.
Yeah,
yes.
Yeah, but to make it bigger, you need to put extra chargers, so you're still moving charges.
Now that is okay. Well, not necessarily though. So let me connect these things together. Yes, his point is, well, you don't have to physically move a charge around. If you just have a charge here and you just put more charges there. Yeah, so you have a knob in there, and you make nature make more charges there. Then nothing is moving, and yet because you're piling up charges, you get a increasing electric field, so a dE dt that is not zero, even though there's nothing moving. Which is a true statement. And Alicia comes along and she says, no. But in order to get those charges there, they have to flow there. So something has moved through space. Yes, that is true, but you are making an additional assumption.
A discontinuity equation that you cannot just transfer some charge.
Exactly. You are making an assumption. So Jort is in principle right. And you sort of counteract that by saying, yes, but there's this additional law that we haven't written down. Namely that, I'm going to say the same thing as you, but in a slightly different phrasing, that there's conservation of charge. Yes. You cannot just have new charges popping out of one location. The only way that to make that work is either because some charges at the other end of the universe popped away there and appeared here. Because if you look at that way, then the whole universe has a conservation of charge, yes? But the statement is stronger. The statement is not just that the amount of charge should be the same in the universe. Why that is actually, we will touch upon later on in the course. Right now we're going to take it as an assumption. In principle, you can have magic wand, you make a couple of charges disappear over there and they pile up over here. That does not break the conservation of charge. But there's a stronger statement. Namely, charges are not just allowed to disappear from space, even not when they pop up somewhere. You actually have to physically move them to get there. Yes? That's a different statement. It means that if let's turn into me. Suppose that there is a conservation of me. Yes? That law unfortunately does not exist, but suppose that the thing existed. Yes? And then I could not break that law by magically disappearing right now and at the same instant appearing at the other side of the door. Forget about speed of light, something going fast speed, forget about all those things. In principle, I do not change the conservation of me if I disappear here and at the same moment appear at the other side of the door. There's a stronger statement, namely, no. If I want to end up over there, I actually have to move through space to get there to begin with. And this is what you meant. We call this the continuity equation. If something has moved, has disappeared from one moment in time to the next moment in time, it must have moved through space. And in fact, I find that so important, I'm going to write it as an extra law here, yes? It's a law that's so important that people don't usually write them as a sort of fifth Maxwell's law, and maybe they should. So what I'm going to write down now is what I'm going to call, say, Maxwell's fifth law. This one. Now let's see if we can read this. Now we really understand what a divergence means. This is just the mathematical expression of what we're now discussing about, me not being allowed to disappear and appear somewhere else in space. What does this mean? D rho d tau. Or d t.
Change of density over time.
Sorry?
Change of density over time.
Yes, but which density?
Charge density.
Charge density, yes. So that means I have a whole bunch of charges here, yes? And it changes in time. So a moment later, I have less charges per cubic meter. Okay? Should equal, let's read now the other side, using that we understand what a divergence means. Stick outiness or so.
The way that the current is sticking out through.
Yes, no, quite literally. I mean, J is nothing else than charges moving through, how many charges per second are moving away, yes? That's what a current means. It's a vector because they move away in a particular direction. Now, how much does that stick out? Well, obviously, if this bulk of charges that I have here is changing in time, then this says, well, then something must have stuck out. Something must have been moving away through space. That's what this thing tells you, right? That's the sticky outiness again of the divergence.
Why is it negative?
Oh, because it sticks away.
Away.
Yes, I mean, if the stick outiness is away from me, that's a plus number. That means that the amount that I end up with here, how much this changes in time, must be a negative number. Yes. If this were a plus, then I'm saying the more I carry away from myself, the more I myself get. So the minus really has a meaning. So this is important. So let's go back to connecting these things to each other. Jort was saying, we were talking about whether these two things were really the same thing. Yes? And then you were saying that was going back to the previous discussion that we were having, that you can make the electric field change in time by just making sure that there's less or more charges at one particular position. And then Alitza countered that and says, yes, but that means you must have had a J somewhere, right? Okay. My question still stands though. Are these two really the same effect? So let me make it, rephrase the question one more time. What we see here, the fourth Maxwell's equation tells you that one way to make an electric field is by shaking about an electric field. Okay? This one tells you can make a magnetic field by having charges go through a wire or move through space. Fine. And it sounds like these two things are the same.
Would you say that if the charge is constant, you still have the first term, not the second one, because the electric field is not changing?
Yes, that is actually, the phrase is slightly different, but that is physically what's going on. Listen, if I suppose, so let me give you a situation where one of the terms survives and the other one does not, right? If we can find at least one of those situations, then obviously those two terms are saying something different. Agreed? So, suppose that I do have a wire here. There's a wire, and I pump a whole bunch of electrons moving through that thing. That will constitute a current. Yes? So this number will certainly not be 0. Will my wire, where I put the charges through, it will have an electric field, because hey, there's charges. Will that electric field change in time? Because that's what this term tells you. It's not about the electric field per se, it's about the change of the electric field. I have a wire, move charges through, it has an electric field. Does the electric field change in time?
If we can have exactly the same number of units of charge with the opposite sign.
Correct. So we're going to say, no, not necessarily. We're going to say that the charge that we push through the wire, let's make them electrons, because that's usually what we do. It's electrons that we move about. and per second we have as many electrons going by. Yes.
So it's constant.
So it's, yeah, we call this a steady current. That's a phrase from electromagnetism. What about the electric field? A wire that you put charges through will have an electric field. Agreed.
Mm-hmm.
Yes. Will the electric field change? Why would it? Because if I look now in time, there will be 5 charges per second flying by, gives me electric field. I look an hour later, and it's a steady current, so I do the exact same thing for a couple of hours. You will still have the same amount of charges flying by, right?
Mm-hmm.
So apparently you can have a situation where yes, there is a current, but no, there's no change in electric field. There is an electric field, but not a changing one. That tells you that these two things are similar, but not the same. Both of them have to do with moving charges, maybe. But one of the terms tells you that even if your electric field does not change, despite the moving charges, you would still have a magnetic field. So this equation is extremely important. It gives you 2 sources for the existence of a magnetic field. All right. I'm going to add another one, just for completeness. You can add magnetic fields and electric fields. I have one magnetic field over here because of some magnet that I put here, and I put another magnet next to it. Yes, they make a combined magnetic field, and it's a sum. It's a sum of their separate magnetic fields. So you can literally just add one of them to the other. That is not obvious. It's a separate assumption. Yes, it's not always true in physics that if you have a certain amount of something here and you put an extra part to it, that the sum will be the total amount. Maybe you can think of examples even. It's an example of physics where you have a certain amount of something, some observable, and you pile on another a certain amount, and the total is not the sum of the two.
Mass of a black hole, when 2 black holes collide.
Okay. That's actually true. Yes.
Isn't it like that with like colliding particles or like nuclear fusion?
Yeah. What about it?
When you like have something like in the fusion, like you're gonna get more or less energy, and there's kind of like a loss or like a mass.
Yes. If you would look at the masses alone, then in a collision in particle physics, the end mass is not the same as the beginning mass. Yes, because energy and mass can be converted into each other. So if you think like a chemist and you have this law that says the causation of mass or something in chemistry, wrong. But this is what it's in chemistry it's true. Yeah, let's be sure there. It's just that in chemistry you usually don't think about things that move at the speed of light. Yes, but in relativity this is not true. But if you just stick to masses alone, yes, then that's a good example. That you have 2 particles and they have a mass and you add them together and the total mass of your remaining particle is not the same. We know the reason. Relativity has sent away some of the mass in terms of kinetic energy or has gained a little bit. That's true. Now forces can be added, yes? If you start pulling on one arm and the other arm, the only thing you have to do to see which one wins is just add them together and see if I end up with a plus or a minus. So that works. Even outside of particle physics, masses generally in Newtonian physics you can add up, right? If I pick up something or whatever, then that mass and my mass together make our total mass. That's fine. Quantum mechanics, maybe an example from there. It's always a good thing if you're looking for exceptions, go to quantum mechanics. Solutions to the Schrödinger equation. Do they add up? So I solve my Schrödinger equation for one part of nature and there's another part of nature and I solve its Schrödinger equation. So you have 2 wave functions in their intermediate region. Do these Schrödinger wave functions, do they add up?
For the same wave equation?
I have one particular piece of nature here and I solve its corresponding Schrödinger equation. I have a piece of nature here. I solve its Schrödinger equation. So in the intermittent region, right, the Schrödinger equation gives you a solution that spreads out over all space. So there is a part where the 2 particles have an overlapping of their respective solutions. Do they add up? No, orthogonal has something to do with eigenstates versus non-eigenstates. And I'm not making such distinctions here. I'm just saying there's a certain amount of wave function here coming from over there. There's a certain amount of wave function here coming from over there. I have their overlapping region. Do they add up?
I mean, you could try to solve Schrödinger equation twice for hydrogen, but if you add 2 electrons to an atom and you get the helium, helium is not just the sum of the 2.
No, that's true. But that's slightly different than what I'm talking about, because at the moment that you have them together, they start feeling each other's interaction, and that I'm leaving out.
Okay.
Yes. Suppose I have a neutral hydrogen system here, not a neutral one, and I, with the magic wand, switch off their interaction, which is not true, because of course they would feel each other's electrons and dipoles and everything. But suppose that you would be able to make them not the systems themselves not feel each other. So you really have 2 separate solutions. Do they add up? Will it help if I write down the Schrödinger equation? So maybe you can see it from the mathematics, maybe. There we go. Is it a linear equation? What do I mean by a linear equation to begin with?
That the variables are not raised to a power that is different than 0 or 1.
That is true. That the thing that you're looking for, in our case a solution, psi or something like that, does not come to higher powers. You might take its derivatives, but you're not allowed to raise it to some power. Now that's true, it's a linear differential equation. Now generally speaking, the sum of solutions to linear differential equations you can add together and still have a solution. It's really quite simple. So suppose that I say I have psi, which is the sum of psi 1 and psi 2, and psi 1 and psi 2 each separately solve this equation. Then if you put this in, then this Laplacian is what we call it, the second derivative, apply to this one. Sure. And then it will also apply to that one. And here's a product of these 2 things. If you put this guy into that, you really just end up with 2 equal Schrödinger equations. Just one of them is only about psi 1 and one of them is only about psi 2. You don't find the psi 2 in the psi 1 equation, you don't find the psi 1 in the psi 2 equation. But if the assumption is that each separately solves their respective equations, then together they solve the whole system. So, long story short, just from the Schrödinger equation alone, you can tell that summing these 2 things is itself a solution. Now, you don't have to actually go through the exercise every time that somebody presents you with a differential equation. The only thing you have to check is whether the thing that you're looking for is only raised to the first power. If that is the case, the sum of solutions is indeed itself a solution. We call that superposition. Now, all of this is only to make you aware that this notion exists. It's not obvious that things in physics can be added up. Quantum mechanics says yes for the Schrödinger equations. Forces mechanics, it's true. I want to give you one counterexample. Suppose, quantum mechanics, I'm not asking whether the wave functions add up. Suppose that I ask you whether their probabilities add up. A psi leads to a probability distribution, right? There's this amount of probability that you find a particle over there, and there's only that amount over there. Do those add up? How does one get a probability from?
Well, you square the psi.
You square the psi. Okay. So you're right. This is our wave function for one particular part of nature. But if you want to turn it into probability that you find a particle at a particular position, you have to modulo square it. Yes, this is probability. Okay. Do probabilities add up? If I have a certain amount of probability for finding the particle here that comes from that system, and I have a certain amount of probability from that system, do they add up to a total probability? Yes, exactly. The question really is here that if you know that psi itself obeys superposition, you can add them up. And we saw from the Schrödinger equation that that is the case. Is it then also true that their combined probability equals the sum of their respective probabilities. Or in other words, is the probability due to their sum, is that equal to psi1 squared plus psi2 squared? Is that true? No. That is not true. Because you're missing 2 times the probability of one and the probability of the other. So here's an exception. Not everything in physics obeys superposition. Right? Wave functions do, probabilities do not. Now we're not going to delve too much into quantum mechanics, but I will only say this. The fact that they don't is why you have quantum mechanics to begin with. Yes? Because interference, that the probability can cancel each other out, is due to this extra term, twice this one and that one. Yes? Because that term can make things smaller and everything. Without that thing, you would not have quantum mechanics in the sense that you can only have particles here and not over there. So all of this is just to tell you that superposition is something that you have to assume from outside. So let's sort of call that Sixth law. Yes, we're going to assume this throughout the whole series, that electric fields and magnetic fields do obey that principle, that you can just add them up. By the way, there's many other counterexamples. Intensity of light, for instance. If I have a certain amount of light from here and a certain amount of light from there, you add them up. Now everybody knows that you can make them sort of counter each other, right? Counteract each other. That would not happen if you could just add the amount of light from the other. Then it could never go to zero or become less. Yes. So there's examples. Now all of this is just to say electromagnetic fields obey superposition. I think that gives us a good starting point. Yes? Any questions on this? Did we cover everything that's on here? Not this so much at this point, but this one we have not done yet. This one's covered. Covered, yes. This was covered, right? Joey, this was you, right? Who came up with this one? Who was it? Somebody came up with this one. That the curl of the electric field is zero if there's no magnetic field, which is of course encapsulated here. Backward. I see, okay. Correct. Accelerating charges emit light. Didn't say anything about this here and now, but we will see this later on in our course. Light electromagnetic oscillation, we will also look into that. And then finally this one we have covered, because this is just a rewrite of the first Maxwell equation. So I think we've covered almost everything. Yes?
Didn't we cover as well that magnetic fields don't do work?
No. Oh, did we? Oh, yeah, please.
Since the magnet, they always have to come back to their cells, and since there's not a movement and placement.
Yeah.
Since work equals is force multiplied by the change in length that they do. And you were saying that a magnetic field always has to return to itself.
Yes.
Since they always go back to
Oh,
the same
no, that is
position.
actually true. Yes. Yes. That also wraps it up. Yes.
Kind of like,
Yes. And I think this is what Alice was originally going for. Yeah, so really the ultimate statement there is that magnetic fields, the best that they can do is that they can change direction, but they cannot add anything to it, right? Work is just a mechanical way of saying adding energy to something via pushing. That's what work is. Now, if magnetic fields do no work because of the second law of Maxwell's equations, then that's another way of saying that you cannot add energy to a system by putting it into a magnetic field. Right? Work is just another way of saying adding energy by pushing and pulling. And apparently this law, and I think I'm just going to paraphrase you now, but this law tells you that the amount of pushing and pulling that the magnetic field does always counteracts itself again. So the amount of energy that you put in by the magnetic field also it takes back. Which is another way of saying that you ultimately have not added anything. And that again is indeed this statement that magnetic fields do not work. Okay, good. All right. Okay, so thank you for the discussion we were having on these topics. Thank you for your input. Now I'm going to be a little bit less freestyle and just walk you through some of the mathematical steps, because as I was saying, you can take the Maxwell's equations as given, but you can almost fully derive them from pure mathematics alone and two experimental facts. Of course, you have to put in something somewhere, yes? So let's do this first with the electric field. So the end of what I'm going to show you is again just going to be the Maxwell's equations, but now hopefully with slightly more understanding still. Yes, this whole today is just meant as a bigger introduction to the Maxwell's equations. Now, let's start with that first experimental fact, and I'm going to do it for electric fields, and then later on we're going to do it for magnetic fields. So let's start with electric fields. At some point people found out that nature has this extra interaction built in, right? At first people of course knew about gravitational interaction, right? Masses like to be together and everything, that sort of stuff. And then people found, you know what? Aside from this number you can assign to objects that says how strongly gravity is pulling on it, some of these things come with numbers that is also a measure of how strong they're pulled. But it's not gravity, there's this other thing going on. Now you all know what I'm talking about, it's the electric field, but you have to understand that back in the day it was completely new that apparently there was some other sort of interaction between particles. Especially because you hardly notice it. Yes? Now I'm sure you as physicists of the 20th century, 21st century, but I was born in 1979 so I still think that I'm in the 20th century. As physicists of the 21st century, of course you know that almost all interactions that you encounter on a daily basis are a direct result of electromagnetism. But think back in the day, yes? Suppose that nobody has ever told you this. You don't know about, small particles of which matter consists. And somebody comes along and says, by the way, did you know that objects also feel each other in a different way than just via gravity? And you would say, well, how is that? Well, there's this other number that you can assign to these things. And if you have done two of these objects, then these two numbers, just like masses, tell whether they should come together or should fly apart from each other. And then you would ask, okay, what is that number? And yes, we now call it charge, but I mean, this book has no charge. Right? The net charge of this thing is 0. The net charge of this pen is also 0. So it's a huge surprise when you suddenly tell people, no, there really is some new number in there. It sounds a little bit like magic. Now why is it, do you think, that even though the electric field strength between particles is very strong, why is it that it took so long for people to find out that it existed in the first place? I mean, you would think that if the interaction is very strong, and electromagnetic interaction is about 10 to the power 45 stronger than gravity, then why is it that we find out about gravity sooner than...
see it?
Sorry?
Because we can't see it.
No, I can also not see gravity, but I can see its effects.
Because gravity does not have like a particle that would annihilate it, like, plus and minus. It can only add together.
That's true. Gravity can only add.
Yes. And electromagnetic interaction is so strong, like if there would be some charges just like randomly flying around, they would...
There we go. Okay. I mean, the first thing that you were saying is completely right. I mean, this new interaction, right, for those older physicists, this new interaction can also push things apart and gravity can pull them together. So in that sense you can see that something else is going on. But my question was slightly different and you answered it. Is, well, if this interaction is so strong, why is it that people only found out about it so much later, right? And the reason is because of its strength. Because if in some way you would be able to get this loose charge hanging around and this other loose charge hanging around, then this extremely strong force between them will make sure that they find each other again and everything gets annihilated again. Yes, well, not annihilated, but the charges add up to net 0. So the strength, if you will, of the electromagnetic interaction also is the reason why it took so long for people to find out that it was there to begin with. Every time that it tried to present itself, the strength nullified everything back to 0. So yes, the book has almost no charge, or has 0 net charge. And if I would be able to get a little bit off of this, like this scrape some electrons off or something like that, then it will almost immediately get some electrons from somewhere and make it and neutralize it again. Everybody's aware of this, right? You stroke a cat and you touch a doorknob or your friend or something like that, you get this electric shock. That's the electric strength making sure that everything gets balanced back again. So people were very surprised when they found that this existed in the first place, but at some point people figured it out. And then they said, well, you know what? We have found that objects come with this extra number, and then this extra number, charge, we're going to call it from now on, constitutes an additional amount of force. And how does that work? Well, again, this is just experimental fact. They found that the amount of force is inversely proportional to the distance between those two charges. Now, this law is what we call Gauss' law. And this is an experimental fact, right? Once you've found out that objects come with additional numbers that say whether they should feel each other or not, and you do some experimentation.
Yeah.
Yes, that's true, but I'm going to turn it into Gauss' law. So for me, it's sort of like the same thing. But you're right. If you want, we can call it Coulomb's law from now on. It will turn into Gauss' law in a moment. Okay, but it's really the same thing. And to add to the confusion, we're going to use a mathematical trick for this, which in mathematics it's a vector integration identity, which in mathematics is called Gauss' law. Okay. And I remember when I was a student and was picking up or hearing about these things for the first time, I had a vector calculus course where I heard about Gauss' law, and I had my electromagnetism course, which happened to be running concurrently, and I also heard about Gauss' law. I said, do they just use the same name? And then later on I realized, no, it's sort of the same thing.
We will also use Gaussian units, or not?
No. There's a unit issue, of course. We're not going to use Gaussian units. Let's not pile up confusion. Yes, confusion also obeys the superposition principle. Okay, you can just add more and more confusion. We don't want that. Okay? So yes, let's call it Coulomb's law for now. But in a moment, it will be Gauss' law. Fine. Yeah. So you found out that objects come with this extra stuff, charge, and that if you put them together, you can just measure how much they make each other accelerate. And then you do this, and you find that if you put them twice as far away, the acceleration that they get from each other is about 4 times as small. This is the 1 over r part, r squared part. Now there's a 4 pi epsilon here. There's really hardly any physics in the 4, the pi, or the epsilon 0. Yes? This relates to your question about units. You can also use units where this is just equal to 1. Yes. Now I'm going to use the SI units. And if you want, you can easily convert it into something else. Then the 4 pi is there. We'll see in a moment why the 4 pi is defined in that way. And there's an epsilon 0. And the epsilon 0 will tell you, as we will also see, something about how difficult it is for electric fields to go through vacuum. Now, again, I will stress, that's a matter of units. If you want, you can use a different unit system where epsilon 0 happens to be exactly 1 over 4 pi if you want, yes? Then all of this is gone. So don't think too much about the units. It's not an issue. All right. The only thing that matters here is experimentally you find that if you have 2 charges together, then how strongly they feel each other has something to do with their product divided by their distance squared. That's the experimental fact. Good. Okay. Now this is enough to get 2 of the Maxwell's equations. That's already in here. My plan is to show you how that works. So, what I'm going to do, I'm going to use what I loosely called Maxwell's 6th equation. This is our little name here, don't use it outside of this classroom. The fact that electric fields obey the superposition principle. Yes. Now first of all, let me just define what I mean by an electric field. And this is a definition. There's no physics involved here, it's just a rewrite of what I have here. The electric field that this particle with the charge Q feels, right? There's some stuff floating about here that we're going to call the electric field. It's a definition matter. It's the result of a big charge Q hanging somewhere else. And then by definition, so I'm going to use this triple equality sign. I just mean definition. The electric field due to the charge, there we go, due to the charge Q, big Q, is just everything except for the small q. Yes. So it's a definitional matter. It's really just this thing written in terms of this new thing that we call the electric field. Now something is wrong on board because this guy is a vector. It should be because the force is a vector, yet I write it as if it's a scalar. This doesn't have a direction. Now again, this experimental fact, the direction in which things are pushed is going to be the direction along the line of the distance between the 2 particles. So that means there should be an r with an hat here. Everybody understands what an r hat means, yes? I'm asking, I'm not testing. R hat means particular direction, but with unit 1, with length 1. The reason that we have these r hats is just another way of saying the only thing that r hat does is tell you in what direction they point. It doesn't add to how strongly it does so. How strongly the force or the electric field is all given by this. And this guy gives you the direction. Okay. Now, let's make a little picture of this. Suppose that I have some coordinate frame. Don't worry, we're not going to talk about relativity just yet. We're going to stick to this coordinate frame for now. X, Y, Z. When I wrote down this, I was assuming that big charge was in the middle of a coordinate system. Yes. And that the other charge, small q, is some distance away. Yes. Now, that you can certainly make this happen. You can certainly just say, well, there's a certain amount of charge in the middle of my coordinate system. You can just use your coordinate system to start there. But generally speaking, you might be looking at a situation where the thing that makes the electric field is all the way over there in your coordinate system, and the thing that feels the electric field is all the way over there, and neither of them are in the origin of your coordinate system. So it would be nice to have something similar like this, but now written when neither of these are in the origin of your coordinate system. Same law, just have to adapt for the fact that we've now written it in only a very special case. So we're going to make this out of it. We're going to say, you know what? Here's Q, over there. We're going to go give that guy a name. In a moment, you know what, let's immediately do it. Let's call this r primed I, because I mean, of all the charges that I could be looking at, I'm talking about big Q I. So its direction from my origin is what I call r vector I. Yes. Now the charge that I want to know how strongly is being attracted or pulled away, small q, is at a different position still. And in my coordinate system, that distance I'm going to call r without an I. Yes. Now, how strongly these two guys are feeling each other has something to do with this distance, right? It should be along their mutual distance. This one is then, using just my basic vector calculus, is just the difference between the two positions of big Q and small q. Now, for the sake, because I've now 15 different r's floating about, let me make life a little bit more simple and summarize the difference between the two particles, the dotted line. That vector I'm going to call capital R. Yes? So capital R is the distance between those two charges. And it's that capital R that should be over here. If I go to the situation where neither of them is in the origin, and I know experimentally that they should feel each other along their mutual distance, then this R should not be that R, this R should not be that R, it should be their mutual distance R. Mm-hmm. Yes? So what I wrote down here was correct, but it's only correct if I happen to have chosen Q in the origin. I'm now going to expand the definition for when big Q is not in the origin. Still the same thing, it's just we have to make sure that we put the right R there. Yes?
This makes sense.
So I'm just making sure that we're not accidentally restricting ourselves to a situation where one of them happens to be in the origin. So this rule is now very general. Good. Okay. Now, this electric field. Yes. But I am now assuming that there's only one of these Q's floating about. I'm interested using this law here, Coulomb law, in how this small q is being pulled or pushed due to the presence of only this big Q. But generally, if I have a particle flying about, he might also feel the electric fields of other Q's, big Q's, yes? So my Coulomb law over there is still not very general, because I'm assuming that there is only one big Q pushing or pulling the thing. And generally speaking, there might be many more. Here is where the superposition comes into play, because you have to add up then all the electric fields coming from the separate big Qs. I really want to stress why I make that point about superposition versus non-superposition. If nature had chosen electric fields not to be summed together, then what I'm going to write down now would be wrong. The fact that people measured that it is not wrong is not obvious at all. Don't make this mistake of thinking, oh, you can always just add stuff together. That works with origins, and it works with, I don't know, forces, all these sorts of things. It works with people maybe. Well, unless they get babies, then it doesn't work anymore. But I mean, in principle, it's not an obvious thing. I was hoping I would get better jokes. It's only going downhill from now. Okay. Next time I'll write down a bunch of jokes and make sure that they get better progressively. So the superposition is really a non-triviality that comes from experiment. But once nature apparently tells us that that is the case, you can easily test it, then you know that the total amount of electric field at the position of this particle, so the total amount of electric field at this R, note my notation, is simply going to be the sum of the electric fields due to the multiple big Qs. So here's another big Q. Over here, it comes with its own little, that one. And then this small charge feels their respective difference. And maybe there's another big Q over here, then that one will have an Ri, and that will influence small q over there. You have to sum all these things together. So I'm going to write it as such. I'm literally just going to sum this rule for the different big R's. Everybody clear what I wrote down here? Everybody clear why I put a little I under the big R? Yes? Obviously, if all the big Q's are at different positions themselves, then the dotted line between that one and the charge that you're interested in is also going to be different, yes? So big R comes with a little I. But the charges themselves do too, because I'm not assuming that this amount of charge is the same as that amount of charge is the same as that amount of charge. So the Q's also come with a little bit of I.
Isn't E squared of Ri?
Yes, you are very right, thank you. Yes. So you would have this. Now let's say that you have a continuous distribution of charges. I'm now assuming that the Q's come in discrete packages. There's a little bit of charge over here, there's a little bit of charge over there, but nothing in between. Which might be true if you think about chemistry or electrons. But if you look at the somewhat macroscopic scale, then usually you don't have a certain amount of charge. Here you have a gradient of charges. Right? It smears out. It's like a water wave. I mean, yes, if you zoom in enough, you can see the individual droplets, but generally speaking, from a big enough scale, it just looks like a bunch of water. Now, if you're going to describe how a particular wave flows by, you can do this by adding all the individual droplets. I think you're better off just integrating over the droplets. So let me draw a little arrow here, and by this I mean if you look at a big enough scale that you cannot see the individual big Qi's anymore, then this becomes an integral. And it would look something like this. I'm integrating now over different Q's. Yes. So it's really just the same expression. It's just this one's continuous and this one is discrete. Now again, it's not very useful to describe macroscopically something in their individual constituent particles. So the dQs here still require me to know where exactly each of these small particles are, but maybe it's much better to have a quantity that tells you how it's distributed over the volume, right? I mean, I'm just talking about the charge density now. How much charge is there per cubic small amount at that location? That's the rho that we already saw in the Maxwell's equations before. Rho, how much charge do you have at a particular location, is literally defined as the amount of charge over there divided by the volume in which you find it, right? It's a charge density. This much charge in that amount of volume. It's a derivative. And if you put that in, then you're able to replace dq by an integration over the volume. So mathematically, it's really just still the same thing. But the nice thing about this new version that I'm writing down now, the nice thing about this new way of writing it is that I'm not just, my integration is not counting the individual small particles, it's now counting the volume. And the volume integral in practice is much easier to do than counting the individual big Q's adding. So it seems like a minor step, but practically speaking, when you want to do the integral, this is much easier, yes? All right, now question. The amount of charge density is of course going to be dependent on where you look, yes? Over there could be more charges on average than over there. Now which of the different R's that I have should I put within there?
I think the R of the line to the little q.
So this one?
Yes.
Yes. Would that be the case or not?
I don't know.
Wouldn't the RI?
Yeah, it would be the Ri, right?
Yeah.
Because,
Why?
what the rho tells you is how much charge there is. Now, let's go through the different R's again, yes. This R tells you where you are calculating the electric field. So this R is where the small q is. That's this R. This is where you want to know the electric field.
Mm-hmm.
The electric field at this R comes about because of the location of all the Q's there.
Mm-hmm, mm-hmm,
Yes.
mm-hmm, mm-hmm, mm-hmm.
How much it then feels that amount, that is given by big R. Because it's the big R that tells you how much they are away from each other. Now,
Yeah.
this is before what we call Ri. Yes, because you have to look at where are the different Q's.
Yes.
And there are different Ri's.
Yes.
Once you know how much Q there is at a particular Ri, so you know how much there is here, then you calculate how far this is from where you are looking, that's capital R, and that is what tells you how strong it feels it. But this guy, this R tells you where is that amount of charge that's making the electric field. Yes? So we have to be careful. There's different R's in there, and you have to be careful which one you use. In fact, it's going to be imperative for the calculations later on. Now, I removed the I again. No. There's a reason. Remember that I was saying that we don't want it. We're not talking about discrete amount of charges anymore. If you have a discrete amount, there's only a small amount there and a small amount there, nothing in between. Then it makes sense to label them charge 1, charge 2, charge 3.
Okay.
But we make this continuous.
Mm-hmm.
Now continuous means that there's all charges everywhere, and all of them influence a small q over here. I'm going to call that one from now on R primed. Yes?
So how did you get this R primed?
It's just a definition. It used to be Ri, but I seems to indicate that I'm looking at
A
individual
one,
ones,
okay.
a specific one. And what I want to do is now I don't want to look at specific ones, I want to look at wherever. So let me draw a picture of this situation. Right, this is just to motivate where you got it from. Let me just draw another picture where you can see slightly in our new notation what it is. Now let's do the same thing here. Here's our Q. I want to know how strongly this guy is being pulled or pushed. This one we call this R. That's that R, because this is where you want to know the electric field. Okay? Around all of this, there is charge smeared about. Not individually anymore, it's smeared out over all space. Now, every point in space comes with a certain amount of how much charge there happens to be. That one I used to call Ri, I'm now going to call R prime. There's no physics there, it's just a relabeling of the notation. I want to drop the i's because it might give you the impression that I'm still talking about discrete distribution of charges, and I want to make it continuous. This is why I changed the notation. So this guy, this distance is what I'm going to call R with a prime. Yes? So I now know there is a certain amount of charge density here at location r prime. It will influence the electric field over here, location r without a prime. And the distance between them we are still going to call what we had before. Yes.
So basically the r prime is just like for whichever you will use.
Yes.
Okay.
So now we're going to integrate. What is the integration over? It's volume, yes? Now let's make things very visual. Suppose over here is the origin of our coordinate system. Yes? Yeah, I'm going to make U the particle Q. The particle Q. Okay? And I'm in the origin here, and I want to know how much he is feeling the combined electric field of all you guys. Yes? So what I have to do, that's what the integral tells me, I have to look at all the individual electric field contributions. So there's a little bit amount coming from you. So in my coordinate system over here, my location towards you is r primed. And your mutual distance is capital R. Yes? So you give a certain amount of contribution to his to the electric field that he feels. Okay, now you're done. Moving on. Going to her. That's a different R primed. Yes? Okay, she's at a different location. You and I are still at a different same location. But there is an R prime between you and me and Dalitza. And you have a different capital R now. And that gives a certain amount of contribution. Done. And I do this with every single one of you.
So we're continuous.
Well, yes, if you huddle very closely.
Okay.
There's only so far I can take this visualization. Yes? But yes, in principle, that's true. I should melt you guys and just make this gooey stuff, and then it would actually be very good. I'm actually much more describing this one than that one, but I don't want to do the melting part. Okay, now, this is what the integral tells you. Integral literally means sweep through the whole volume, look for all the individual charges, find how much Jan feels each of your electric fields, add them together. That's literally mathematically what the integral tells you what you should do. That's what this guy tells you. That's all there is to it.
So in this case, would the volume be a triple integral of the spherical?
Yes. Yes. In my, whether you use spherical integral or Cartesian, that is highly dependent on which happens to be most practical, yes. But it is a three-dimensional one. Because in our particular example, you're sweeping over you guys, right, to get all the combined electric fields on his position. Happens to be only in 2 dimensions because you are sitting at 2 dimensions. But if somebody decides, if we're always going to take into account all the guys sitting upstairs and downstairs, there's a 3rd dimension. So this is an integral over all of space. Now, in previous iterations of this course, I tended to call r primed the sweeping coordinate, because it's literally what it does. It's like a lighthouse beam, sweeps over all the volume, picks out where charges are, calculates a piece how far away they are from Jan, then calculates the electric field, and this adds them up. So I'm going to call this the r prime, the sweeping one now. It sweeps over volume, picks out the contribution.